Well, hello everybody. This is a problem that was sent to me by a student from within MathXL, and I've copied it here in a bigger font. And it's interesting because this problem provides me an opportunity to really reach back into the past and reach forward into the future. It's an excellent problem that allows us to sort of gut check where you're at right now in the course and see if you're getting these major ideas down. Now, it asks us to simplify and assume x can be any real number. Now, the idea here that I've been sort of hammering on traces back to very early in the course when I introduced not PEMDAS but PERMDAS. I changed it, if you recall. Now, this was the classic way of a mnemonic device to memorize the order of operations. And it was normally said PEMDAS, and I put in this R. And the reason is really for this moment now. I mean, essentially, these guys, addition and subtraction, are inverse operations. They undo each other. They're opposites. They're like brother and sister. And so too with multiplication and division. They're inverse operations. They undo each other. And so to just have PEMDAS was to leave the fact behind that it also has a sister or brother operation, an inverse to itself. What undoes exponents is roots. And so that's why we have changed it to PERMDAS. And that's exactly where we're at right now. We have exponents and we have roots. And if this problem right here that we're looking at just consisted of, let me just pretend, let's just cover this up for a moment. If it just consisted of that, then what would happen here is the sixth root would literally cancel the sixth power. They're opposite operations. They undo each other. And in fact, we would be looking at a simple solution here, right here, if that was the case. But of course that 64 does exist, and so we need to deal with it. But before I do that, I wanted to say one more thing about this PERMDAS, and that is why I think it's such a great structure. There's actually two more operations that we can put in there, and I'd put them, say, up here because in a sense it's what you're aiming towards in the future. The D stands for differentiation, and the I stands for integration. And these two operations are the fundamental operations that you'll meet in calculus. And they are, in fact, inverse operations of each other. They undo each other. And as a matter of fact, the idea that they're inverse operations is called the fundamental theorem of calculus. So it's a very nice structure because it gets you thinking in terms of inverses and opposites. And that's what math is all about. I mean, I say all about, but certainly whenever there's a new mathematical object or a new mathematical operation, you want to find out if it has an inverse. Now, for instance, very shortly we're going to be dealing with ordered pairs. That's a mathematical object, and naturally a mathematician would wonder, does that ordered pair have an inverse? And we'll be there within a couple of chapters. For now, I just want you to think about that. What would be the inverse of an ordered pair, like 2, 1? So that's the deeper idea that's flowing through this problem right here. That exponents undo roots, roots undo exponents, and they're inverse operations. Now, so what I need to do is really tear 64 apart. And that harks back to an idea that we haven't much covered in this class because it's assumed that you got a good treatment of it in a preceding class. That's the idea of a factor tree. Now, here is me tearing apart 64 into what's called its prime factorizations. And I'm building here a factor tree. 2 times 32 will get me 64. 2 is a prime number. It can't be simplified, but 32 can. And so I broke it up as 2 times 16, and then 16 is equal to 4 times 4, and then each 4, of course, is equal to 2 times 2. And the reason why this is called a factor tree is because, well, I know, think of it like this. This tree is like that. This is a trunk. It's an upside down tree, and there's the trunk. And the main idea here is that when you do this, and you simplify it down to its prime atoms, the leaves of the tree, right here, form the prime factorization of the number. And as you can see, there are 6 2's right here. And in fact, the prime factorization of 64 is 2 to the 6. So let's show that in terms of exponents. There's 2 to the 6. That's the prime factorization of 64. And here's another interesting idea that's going down here that doesn't get much play. Suppose I had factored this another way, like this. I had torn it apart this way. Notice my first bifurcation here is to say, well, 64 is equal to 8 times 8. And then the 8s are equal to 2 times 4. And then these are leaves, they can't be factored any farther, but 4 can, and so I do that. Notice you get the same prime factorization. What we have here are, in fact, 6 2's. And so the greater idea here, and this is actually called the fundamental theorem of arithmetic, is that the prime factorizations of a number, no matter what path you take to get there, are the same. They're unique. That's called the fundamental theorem of arithmetic. So some interesting fundamental ideas operating here in this pretty simple problem. So what we've discovered is that 64 can be rewritten as 2 to the 6th, and that's my first move here. And of course this is all very nice because the 6th root will undo 6 powers. And what I'm going to do here is actually write this as what I call a house divided. It's an extra move, but I just want to show that particular move, that you can. Here is the house, and I'm sort of breaking it up into 2 houses that are linked by multiplication. And I'm doing this because I really want to emphasize the fact that the 6th root undoes the 6th power. The 6th root undoes the 6th power. And of course all we have left here is this. Definitely a simplified version. And the question is, are we done right now? And the answer is no, not quite. Because the problem says that we are to assume that x can be any real number. So it's not quite kosher for me to say that this on the left, this bit here on the left, this expression on the left is equal to this simplified version of the expression here on the right. And you could see that if you were to let x equal some negative number. For example, if x was equal to negative 5 here, you'd have a negative 4 then. Negative 5 plus 1 is negative 4 times 2, which would be negative 8. So this would be a negative 8 on the right hand side. If you let x equal negative 5 here, you'd get again negative 4 to the 6th power, which would end up being positive. And so the negative would disappear and there are no more negatives to flip it the other way. And so you'd end up with a positive left hand side and a negative right hand side. And so that's why we want to utilize the idea of absolute value here and enclose this part right here so that there's no question that we don't create a negative instance there. Now I treated that in another video, which I'll put the link in, and if you are at all confused, I definitely get deeper into it with this video here. Well, I think that's it. A quick summary. Let's talk about this. The ideas here, I mentioned the fact that instead of PEMDAS, we're talking about PERMDAS. And we had this interesting idea towards your future, I hope, if you head towards calculus, that there's 2 new operations, differentiation and integration, and that those 2 operations are inverses of each other, and together that fact that they're inverses of each other is called the fundamental theorem of calculus. And then we had the idea that when you break a number apart into its prime atoms, those prime atoms are unique to that particular number, and that was called the fundamental theorem of arithmetic. And as you notice here, we're covering a lot of territory with a pretty simple problem, but there's a gap there between calculus and arithmetic, and you might be wondering, is there such a thing as the fundamental theorem of algebra? And indeed there is, and we will touch on it in the next chapter, barely. You'll get a healthier dose of it in college algebra. So there's some tantalizing fundamentals, and I'll be talking to you again soon. Thanks for listening.